Next topic is the stress strain diagram, that is the part of strength of material. The contents are the stresses, principal stress, strain, generalized Hooke's law, Poisson ratio, modulus of elasticity, and stress strain diagram. Now, what is the stress? Basically, it is the resistance offered by material against deformation is known as the stress. When a certain force is applied on the body deforms. The way in which body deforms depends on the type of loading. Now consider a beam, consider a cylinder in which compressive load is applied. The original length is L and area is A. When we apply the compressive load, the body cylinder will shorten by amount X. So compression will take place. That is the direct stress. Another case is, second one is cylindrical solid shaft type. One end is fixed and tensile load is applied on this end. By applying a tensile load, the body elongates by an amount X. It means the tensile force makes the body longer and compressive force makes the body shorter. Shear stress is the type of stress which force is applied sideways on the material. It means when this load is applied on this edge, the material will deform in this shape. This is the shear stress, that is the force is applied side by on the material transversely. Next is the stress. Stress is the basically stress at a point. Stress at a point is defined by 9 components. Consider certain body, X this coordinate, Y, Z, these are coordinate axes. This is if we consider this plane, that is YZ plane, the stress at this point is sigma XX, at this point is tau XY, at this point is tau XZ. This is the YZ plane. It means sigma XX, in which first subscript defines the plane in which the stresses are acting. Second defines the direction of that component. X is, it means normal to plane. It means the stress is acting in the YZ plane and in the X direction. So sigma XX denotes the X denotes the YZ plane and X denotes the direction. Similarly, tau XY, X defines the plane and Y defines the direction in which the stresses component are acting. At any the stress component on any arbitrary plane are computed using Cauchy's stress formula. That is given by tau x n equal to nx sigma x plus ny tau yx plus nz tau zx. This is basically nx, ny and nz defines the direction cosines. These are the direction cosines, and sigma x, tau yx, tau zx are the stress components. Now normal stress and shear stress. Now consider any arbitrary body on which x txn acting in the extraction, tyn component ty n is acting in the y direction, tzn is acting in the z direction. Now if we compute the resultant stress that is also given by txn square plus tyn square okay. Now the resultant stress, one component act along the normal and other act along the tangential direction perpendicular to that direction. The component, this is known as the normal component, this is known as the shear component. The resultant stress is also computed as T n square equal to sigma n square plus tau square. Sigma is the normal and tau is the shear stress acting. Principal stresses, basically if we consider a point P, one plane is passing like this, second plane is passing like this, third plane is passing like this through this point. So if we draw planes through a point, there are infinite number of planes passing through a point. Thus plane on which the resultant stresses are wholly normal stresses and shear stresses vanishes, that means the component of shear stress is 0, that plane is known as the principal plane. The whole stresses are normal stresses, shear stresses are 0. Sigma, let there is a plane with n traction cosine nx, ny and nz on which the stress is wholly normal, sigma be the magnitude of resultant vector. Now the component of this along x, y, z, that is sigma x, sigma y, sigma component of this along x, y and z axis. By using Cauchy's stress formula, if we substitute the value of Txn in this equation, value of Tyn in second equation and Tzn in the third equation, on solving simultaneously these three equations, that is we will get sigma x minus sigma, sigma y minus sigma, sigma z minus sigma, tau xy, tau xz, tau yx, tau yz, tau zx, tau zy. These are the direction cosines equal to 0. If we solve these three equations, we will get three value of stresses. That is sigma 1, this is the cubic third order equation. So we will get three values, sigma 1, sigma 2 and sigma 3. These values are known as the principal stresses. Other way of solving this is also we compute the stress invariant. Stress variant I1 is given by the sum of diagonal elements sigma x plus sigma y plus sigma z. That is sigma xx plus sigma yy plus sigma yz. Now second stress invariant is computed by computing determinant of this matrix plus determinant of this matrix plus determinant of sigma z, tau xz, sigma z. This will give I2. I3 is the determinant of the whole matrix sigma. This is the cubic equation. After solving this equation, we will get three values of sigma. These all three values are known as principal stresses. Strain, as we applied a load on certain object, certain body, it as load is applied, there will be deformation will occur in the body. Consider a case, we applied a compressive load F. The body shortens by an amount X. So at that moment the body is here. So strain is basically the change in length per unit original length. Change in length is X, original length is L. So strain at point is defined as X per unit length. As strain has no units, since X is also in meter, L is also in meter, so it is a dimensionless quantity. Similar way, in a similar manner, the strains are defined in different way: normal strain, shear strain, volumetric strain. Strain at a point is defined by 6 components as defined by, as in case of stress is defined by 6 component. The strain component sigma epsilon xx first defines the plane, second defines the x direction in which the strain is acting. This is also in same manner. Shear strain, if we applied a load F in this direction, original shape of the body is this. As we applied the load, this will deform from its original position to the another position, that is original position is A, B, C, D, C dash, D dash. Original position is A, B, C, D. Now it deformed to A, B, D dash, C dash. Shear strain is defined as the distance moved to the height. Distance formed to the height. That is given as the this gamma is x per unit. Original length is L. In order to develop a relation between stresses and strain, generalized Hooke's law is used. Generalized Hooke's law, the six strain components are related to six stress component. A material is said to be homogeneous if it has same composition throughout the body. Hence the elastic properties are same at every point in the body. The properties need to be same in all the directions for the material to be homogeneous. But in case of isotropic material, the material properties are same in all the directions. But in case of homogeneous, it is not the case. A material is said to be isotropic if it has same elastic properties in all the directions. In an isotropic material, the number of elastic constants are 36. In orthotropic, elastic constants are 9. In isotropic material, the constants are reduced to 2, that is Young's modulus and Poisson ratio. Hooke's law, most engineering materials exhibit a linear relationship between stress and strain within the elastic limit. The relation between stress and strain up to the proportionality limit is given by Hooke's law, discovered by Robert Hooke in 1676 using something known as Hooke's law. The value of the E represents the constant proportionality is known as Young's modulus. Now Poisson ratio. Now consider if we applied a load, this much elongation will occur. The diameter reduces by this amount. That is the ratio of the, if we applied a longitudinal load on a certain bar or rod, its length will increase and diameter will decrease. The ratio of strain in lateral direction to ratio in the strain in axial direction is known as the Poisson ratio. The dashed line represents the shape before loading, and solid line gives the after loading. Poisson ratio is discovered by mathematician Simon Dennis Poisson, who attempted to calculate the ratio by using molecular theory of material. The value of Poisson ratio is given by this minus delta D is the change in diameter to the original diameter, delta L is the change in length to the original length. Modulus of elasticity. Elastic material, when released, returns back to its original position. They also obey Hooke's law. This is the law of spring, which states that deformation is directly proportional to the force. The stiffness is different for different material and different sizes of material. We may eliminate the size by using a stress strain instead of force and deformation. As we know that force is sigma into area, x is epsilon L. If we compute F by x, that is sigma E epsilon L. F by x is known as Young's modulus of elasticity. Stress strain diagram is obtained by plotting the various values of stress and strain and corresponding conventional stress strain diagram. We can determine the nominal or engendering stress by using a relation sigma equal to E by A, and A is the area that is the original area of the section that will remain constant. This is the characteristic stress strain diagram for mild steel. Mild steel is also known as structural steel or low carbon steel. Structural steel is basically used in the building, bridges, tower, and many other applications of construction. Strains are plotted in the horizontal axis and stresses on the vertical. The diagram is in the straight line as shown in the next slide. The diagram is in the straight line from O to A. This is known as proportionality limit. In this region, stress and strain are directly proportional to, and the behavior of material is said to be linear. Beyond point A, that is beyond point A, this point is A, this point B, this point is C. Beyond point A, the linear relationship between stress and strain no longer exists. Hence, the stress at A is called proportional limit. With increasing load beyond the proportional limit, the strain begins to flow more rapidly for each increment in stress. The stress strain curve then has a smaller and smaller slope until at point B the curve becomes horizontal. Beginning at this point, considerable elongation occurs with no noticeable increase in the tensile force from B to C. The phenomenon is known as yielding of the material. The stress at point B is called the yield stress. In the region from B to C, the material becomes perfectly plastic, which means that it can deform without increasing the applied load in this section. The elongation of the mild steel specimen in the perfect plastic region is typically 10 to 15 times the elongation that occurs between the onset of loading and proportional limit. After undergoing large strains, this point is CD. After going large strain that occur during the region BC, the steel begins to strain harden. During strain hardening, the material undergo changes in atomic and crystalline structure, resulting in increased resistance of material for further deformation. Thus, additional elongation requires an increase in the tensile load, and the stress strain diagram has a positive slope from C to D. The load eventually reaches its maximum value and is known as the ultimate stress. Further stretching of the bar is by reduction in the load. Fracture point occurs at point at this point. Point fracture occurs at this point. Necking is basically the reduction in area of the bar becomes clearly visible and pronounced necking of the bar occurs. This is the necking. The conventional stress strain diagram is this one. True stress strain diagram. True stress strain diagram is the value of the stress is higher as compared to conventional because stresses are force per unit area. In case of true stress diagram, the original area of the cross section is used, which is decreasing, and therefore the corresponding value of the stresses are increasing. True stress diagram, instead of using original cross section area, we use the actual cross section area length at the instant of load is measured. The true stress is longer than nominal stress because it is calculated with a smaller area. Value of stress strains calculated are called true stress and true strain. And a plot of their values is true stress strain diagram. This is shown in the last slide. Ductile materials that undergo large strain before failure are classified as ductile material. Advantage of ductility is that visible distortion may occur if the load comes too large, thus provide an opportunity to take remedial action before the actual fracture occurs. Such material, mild steel, ductility of material is to for the percentage elongation or percentage reduction in area at the time of fracture. Percentage elongation is the LF minus L naught by L naught. LF is the final crack length. Distance between the gauge marks at a fracture. L naught is the original gauge length. Percentage reduction in area. A naught is the original cross section area. AF is the final area at the fracture section. Most metals do not exhibit constant yielding behavior beyond the plastic range, aluminium. It does not have well-defined yield point. This is the standard practice to find the yield strength using a graphical procedure called offset method. Generally, in case of aluminium, the does not have yield point and yet undergo large strain after the proportional limit. And undergo large strain after the proportional limit. In order to compute the yield strength at a point 2%, draw a line parallel to this, and at a point where this intersects this curve is known as the yield strength of that material. This is the procedure for computing the yield strength in case of aluminium. Brittle material that fail in tension at relatively low value of strain or classified as brittle material. Examples are clay, cast iron, glass, stone. These materials fail with only little elongation after the proportional limit is exceeded. and the fracture stress is the ultimate stress. Ordinary glass is nearly ideal brittle material because it actually will no ductility. This is stress strain diagram for the aluminium alloy. This is the stress strain diagram for the brittle material, that is glass in which no ductility occurs. Strain hardening. If a certain specimen of a ductile material is loaded into the plastic region, then after that up to point A dash it is loaded. Then it is unloaded. The elastic strain is covered as the material returns to its equilibrium state. Now we will draw a line parallel to this. This is known as elastic recovery. These are the permanent stresses that are developed. Plastic strain remains the material subject to permanent set. Specimen loaded point A to A dash. Interatomic forces have to be overcome to elongate specimen elastically. These same forces pull atoms back together when load is moved. Since E is the same, slope of line O dash A dash is same as that of line OA. During unloading, the bar returns partially to its ringer shape. Material is partially elastic. This region is known as the plastic. This is elastic. Now stress strain diagram has a higher point as a result of strain hardening. This is the relationship between three elastic constant. First is elastic modulus, the ratio of elastic stress to elastic strain of a material body is called the elastic modulus. Shear modulus, ratio of shearing stress to shearing strain of a material body. Bulk modulus is the ratio of volume stress to volume strain of a material is called the bulk modulus. Now the relationship between E and G is given by E equal to 2G 1 plus nu. G is the shear modulus, E is the Young's modulus, nu is the Poisson ratio. Relation between E and K. E is elastic modulus, K is bulk modulus. E equal to 3K 1 minus 2 nu. Relationship between Young's modulus, shear modulus and bulk modulus is given by E equal to 9GK 3K plus GG. Now we will solve certain problems. The following data related to bar subjected to a tensile test. The diameter of the bar is 30 mm. Certain bar. Diameter is D, length is L. Bar is subjected to tensile load. Then it will deform to this shape, diameter shorten, and delta L is the increase in the length. Diameter bar is 30 mm, load is 54 kN, gauge length is 300 mm, delta L is 0.112 mm, delta T is 0.00366 mm. We have to compute the Poisson ratio. Poisson ratio is given by changing rate of strain to the longitudinal strain to delta L by L. We have to compute delta D by D, that is 0.00366 by 30. This comes out to be 1.22 into 10 minus 4. and delta L by L comes out to be 3.73 10 to the minus 4. So nu comes out to be 1.22 divided by 3.73 comes out to be 0.327. Now E is stress per unit strain. Stress is force per unit area. Strain is delta L per unit length. This comes out to be 2.05 into 10 to the 5 meganewton per meter square. As we know that E equal to 2G 1 plus nu. G is E by 2 1 plus nu. The value of shear modulus comes out to be 0.7 into 10 to the 5 meganewton per meter square. As we also know the relationship between E and K, 3K 1 minus 2 nu. The value of K is E by 3 1 minus 2 nu. This will comes out to be 1.97 into 10 to the 5 meganewton per meter square. These are the value of the three moduli. Now, in the second column, concrete column of cross-sectional area 400 by 400 mm, that is 0.4 meter into 0.4 meter cross-section area. So cross-section area of column is 0.4 into 0.4, that is 0.16 meters square. Is reinforced by 4 longitudinal 50 mm diameter round steel bar placed at each corner. So area of each steel bar is pi by 4 d square. That is number of bars are 4 into pi by 4 into 0.65. This value comes out to be 0.00785 meter square. So area of concrete is given by area of column minus area of steel bar. This is point. If a column carries a compressive load of 300 kN, if you applied a compressive load, the strain in steel bar equal to the strain in the concrete. It means strain in steel equal to strain in concrete. That is sigma S by ES equal to sigma C E C. It means sigma S equal to sigma C ES by EC. The value of Young's modulus of steel is 15 times that of concrete. Sigma S equal to 15 sigma C. Now the load shared by steel bar and concrete is 300 kN. It means PC plus P steel 303 Newton. P is sigma C AC plus sigma S AS 300 into 10 Newton. Now, if we substitute the value of sigma S in terms of sigma C, sigma S in terms of sigma C, AC and AS, we will get the value of sigma C from this equation. That is comes out to be 1.1 meganewton per meter square. Now, sigma steel is 15 times of sigma C. So this value comes out to be 15 times of 1.1 meganewton per meter square. This is 16.65 meganewton per meter square. Now next is to compute the load carried by steel bar. Load carried by steel bar is PS sigma s AS. Sigma s is 16.65. Area of steel bar is 0.00785 into 10 to the 6 meganewton per meter square. Load comes out to be kilonewton. Load carried by concrete sigma c AC. Sigma c 1.11 into 10 to the 6. Area of concrete is 0.521, that is 169 kilonewton. So load carried by steel bar is 130.7 kilonewton and load carried by concrete is 169 kilonewton.